Okay, so let's move to the second section in lecture two. We call it electron migration, which means that you apply the electrical field on on these materials. Also means that you connect your materials to the battery. Okay. So first of all, we will explain the physical concept of electron migration, the effects induced by electron migration, which means that some effects uh, due to you connect this material to the battery or acting the electrical potential gradient on it. And then we will show you how to quantify the electron migration effects. And because we need to show you how to estimate or quantify them, so there are two examples here. The first one, the materials we deal with is ionic conductors. So we are going to investigate the, the atomic flux of these interstitial charge ions in ionic conductors when you connect this to the battery. And the second choice will be the second example here we will discuss what happens when the atomic flux of interstitial or substitution atoms in metals. Then before we end the sections, we are going to talk about the two cases, typical cases uh, caused by these electron migrations. And both of them are the both of them are electron migration induced failure in device. The first one we call the Blatch effect. Also, some people call it as a short stripe effect. This is the major effect and also have side effect, the secondary effect. So people call it as a current cloudy effect. Both of them were um, were induced or cause lots of void formation that will lead the failure of our device, especially happen in the conducting line in our device. So as long as you learn what are they, then we have chance to avoid this effect. So this is the most important part in these sections. So let's move to the first one, uh, the first case, which happens in ionic conductors. Okay, so we are going to talk about the mass transport under electrical field. This is EM, okay? Electron part actually is everything happens when I acting or apply the electrical field on our materials. But the material system we have here is we have ionic conductors, ionic materials, but they belong to ionic conductors, which means that we have the charge ion passing through these ionic materials. So this is why you can call it as a conductors. And the applications for this ionic conductor so far actually is the solid ionic conductor electrolytes in solid state battery. So people want to actually scientists develop different types of ionic conductors serve as an electrolyte in solid state battery for safety issues, as you know. Okay, so what we have here is we have ionic materials that contains a dilute concentration of positive charge ion that diffuse interstitially. So what we have here is we have ionic materials. So here probably we use the zinc sulfate as ionic materials. And inside these materials, we also have a dilute, is quite important, dilute concentration of positive charge ions. We have positive charge ion and it moves through interstitial side. So we call that diffuse interstitially. So we have a positive charge ion. Here is a copper with two positive charge and at interstitial side. So as long as I connect to the battery, so So this positive copper ions will can move through interstitial side. Okay, so under these conditions, because we already connect to the battery acting an electrical field on these materials. So um, let's estimate what's the driving force flux of this interstitial, which means that the positive copper ions, and what is the electrical conductivity of these ionic materials. Because you have a dopant, right, which is the positive charge, as long as you apply a battery or connect to a battery, then this positive charge ions for sure will move through these materials, and that will cause the the current. So you can estimate you have chance to estimate the electrical conductivity of these materials. So in order to answer these questions, so we need to step by step. The first one, you need to write down what's the driving force in the systems. Driving force. So the driving force here usually can be rewritten as negative potential turns gradient of potential. And potential here, you have how many driving force? You have possible driving force inside this material. The first one for sure, probably you will say, oh, professor, I can connect this to the battery. Yes. So you do have an electrical potential gradient. Yes. And you also have a dopant. So probably there's a chemical potential gradient. Okay, so two possible driving force here. So the potential turn have the chemical potential. One here means this interstitials, this positive charge, plus this positive charge ion moves through under this electrical field. So the potential would be the charge times the electrical potential. Okay, so you have a Q times this phi. You got the potential turn. This is due to this charge ion moves through this electrical field. Okay, so if you have some concern about this, so probably we do have one slide for your reference. This some kind of review. Um, this we call the final goal. Actually, I want to know the potential, total potential inside this material system. But inside this material system, we do have two components or two parts. The first one is we have a chemical work due to probably a concentration of our copper ion will be different. So we call it chemical work. And the second term actually is the electrical work due to I connect this materials with battery, or I apply an electrical field acting on these materials. We have phi. Okay, so the potential electron chemical potential included the chemical work turn, and also electrical work turn. Okay, so consider we have a mass transport. Here is a copper ion of a ionic systems. So one intrinsic constraint would be the total change in charge equals to the charge Q1 times the C1 is a change in concentration. Depending on how many positive copper ions moves, and it carry charge Q1. So I do have a total charge change dq. Okay, so we need to submention all the potential. In order to get the total potential, you need to submention all potential functions with its entity. So we have a potential function times its physical entity. So potential term, first one would be, probably the second one would be more easier to use, is a chemical potential of this for that copper ions, and the the concentration changes in that copper ion, we have a mu1 times the C1. This is uh, for the chemical work turn. And the other is this copper ions moves through this electrical field. So we have the phi. This is electrical potential times the total charge change. Okay, because this will be depending on how many copper ions moves through this material. So the total charge change, we have a Q1 times dC1. So we can take all the C1 all the C1 outside. So we have a mu1 plus Q1 times phi. And this is we call the potential, total potential. Based on here, we know the driving force here is for the atomic flux will be we take the gradient for this one. So we take the driving force for the ion will be the take gradient for potential term. The potential here you can interpret as the chemical potential plus this term is induced by the electrical field you acting on this material will be the Q1 phi. So compare here, this can be a potential term. So this term included a chemical and electrical potential. We call the electron chemical potential. You take the negative gradient on this potential term is a driving force. Okay, so back to prior slide. So the potential term included the chemical potential of this copper ion, and extra term is due to you apply electrical field on these materials, and this positive, uh, these copper ions probably will be moves through this material, and Q1 is how much it carry, how much charge it carry times the phi is the electrical potential you acting on these materials. We got a Q1 phi. So now I have a driving force, right? So what's the flux of this copper ion interstitials? The flux actually can be write down as, oh, okay, so this is just Q times negative electrical potential gradient. So this is for help you to understand why I write a Q1 phi, okay? But what's the atomic flux here? Because this flux actually, the atomic flux, we do have two driving force. The first one is chemical potential gradient. The second one is due to the electrical field, electrical potential gradient. Because I acting on this material. So the first term is due to the chemical potential gradient. It's obey the fixed first law, so be negative diffusivity concentration gradient is due to the first term. Is due to the chemical potential gradient equals to obey fixed first law negative diffusivity concentration gradient. And the concentration gradient for sure is a concentration gradient for this copper ions. And the second term due to the electrical potential term, actually it'll be, you can easily remember, so you can just follow me, will be mobility, concentration, and also driving force is negative charge times electrical potential gradient. So it's mobility, concentration, and driving force. Q1 electrical potential gradient. So because this is constant, you can take it out. So we have a negative electrical potential gradient. So now I already write down the atomic flux for this copper in iron, which is served as interstitials, can be written because it's driven by chemical potential gradient and also electrical potential gradient. For electrical term, we use the mobility, concentration, and driving force. So now I already know the flux of interstitials. The unit for this is the numbers of copper ions passing through a specific area during specific time period. But the current actually is due to, if you can measure the current passing through this materials due to this interstitial, right? So the electrical current density of these materials after I applying electrical field would be the current density equals to the charge these materials, this ion carry times the atomic flux of these interstitials. So Q1, J1. So I use this 2 times the Q1 will be the current density I'm going to measure passing through these materials, right? So, and also based on the Ohm's law, I can get it will be equals to electrical conductivity times the negative electrical potential gradient. So I use this 2 times the Q1. And in order to simplify these equations, I make a very important assumptions. In the absence of significant concentration gradient means that the concentration, because it's dilute, so I can assume concentration gradient is quite small. So I can delete this term. So I use this term 2 times Q1. So I got this results and compare with the Ohm's law. So I can get the conductivity of this ionic conductor, which means is the doped zinc sulfate equals to this D1 divisibility of this copper, concentration of these copper ions, and the charge the charge carried by these ions square divided by kT. So based on these results, we get the electrical conductivity of this doped zinc sulfate equals to this. Okay, so so if you want to increase the conductivity of this ionic of this zinc sulfate, either you can you can increase the concentration, increase the divisibility of this copper ion through the inside this materials, or increase the charge carry on these copper ions. Either way, or you can increase the electrical conductivity of these materials. Okay, and if you zoom out, what we have we have learned in this slides, we successfully to interpret the conductivity of these doped ions by what? Because by we formulate the driving force, get the flux of these interstitials, and use these interstitials to times the charge it carries. So I can estimate the current, electrical current density. And based on all this, I can get the electrical conductivity of these materials. And also, in the meantime, I also have chance to increase the conductivity of my interest in ionic materials for less applications, for allow them to used in solid state battery, used as a conductor electrolyte in solid state battery. Okay, so this is also the one possible applications for electron migration. But for this one, it's not a negative or drawbacks when we talk about in ionic materials. Okay.